All right. Hello, everybody. And thanks for joining us for this DevSummit talk on Project Magma, an open source mobile core that sits in the Linux Foundation as an open source project. My name is Mark Meunier. I am a part of the ARM infrastructure team, and I'm also sitting on the board of governance for the Magma project. Govind?
Hi, I'm Govindarajan Mohandas. I'm an engineer in ARM. I'm also a TSC member in Magma Core Foundation.
Shubham?
Hi everyone, I'm Shubham Chaturmasi. I'm currently working as a DevOps engineer with Magma Core Foundation. I'm also a member in Technical Steering Committee for the Magma project. Thank you.
All right, we'll kick it off. To start, we're going to pass it over to Govind and go over an overview of the Magma project. Take it away, Govind.
Thanks, Mark. So today I would like to discuss the Magma architecture details as well as the steps to build your own cellular network using Magma. In this picture, you see the major components that are needed to build a cellular network, and those components are RAN and mobile core. The RAN comprises the cell tower and E node B in the case of 4G and G node B in the case of 5G, with which the user equipments like mobile phones and customer premises equipments and IoT devices connect through the wireless technologies like LTE, 5G, and 6G in the future. The mobile core provisions the cell tower with E node B or G node B and the user equipment. It is the brain of cellular network. It establishes the networking connections between the user equipment, RAN, and the internet. Traditionally, the cellular network is built using the networking equipment from big players. These equipments are expensive to deploy in rural and sparsely populated areas. As per 2021 GSMA report, 3.8 billion people in the world don't have access to internet. So how can we provide internet at low cost in those unserved geographical areas? Magma is one of the solutions. The goal of Magma project is to provide internet connectivity in rural areas at a low cost. Thanks to Meta for taking this initiative. And Magma is an open source mobile core. As you see in this picture, the blue box represents the mobile core. And as I said, it is the brain of the cellular network. So because it's an open source mobile core, you can build commercial grade, do it yourself wireless networks. So Magma mobile core can be run on any COT server or any device of any form factor, ranging from Raspberry Pi all the way till AWS Graviton instances. Magma is agnostic to wireless access network. What it means is it can support different wireless technologies like LTE, 5G, and even Wi-Fi. The interesting part is you can run the mobile core anywhere. It can be run in cell tower premises itself to create local breakout points with terrestrial or satellite backed internet backhauls. It can be installed in large campuses or even factories to provide cellular connectivity using the free unlicensed CBRS spectrum to devices that can support SIM and eSIM. Now let's discuss about the high-level architecture of Magma. In this picture, you see there are three components. One is access gateway, and the other one is orchestrator, and the last one is federation gateway. The AGW, which is the access gateway, it implements the traditional evolved packet core of LTE. It comprises the serving gateway, packet gateway, and mobility management entity. You can see SGW, PGW, and MME in this AGW box. The AGW can be installed in any remote locations, and it can work with any radio of your choice to create the local breakout points. It uses Open vSwitch to provide the data plane functionality, which is again an open source software. The AGW is currently tested on Ubuntu operating system. Now, let's say if you're camping in a national park or you are in an island with no cellular coverage, you can build your own cellular network using Magma with satellite backhaul. All you have to carry with you is a device like Raspberry Pi or any ARM ODM partner systems, which will be like introduced by Mark in a few more minutes. And you can carry those to run the AGW in it and an indoor or outdoor radio of your choice to the remote area and create your local breakout point for cellular connectivity. Now the next component is Orchestrator. Orchestrator provides the network management system interface to create the LTE or 5G network. What it means is to create the LTE network, you have to add the eNode B and AGW devices as part of the LTE network. This orchestrator can run on a remote location like AWS Cloud, and you can use the NMS page to monitor the LTE or 5G network remotely. The last component here is the Federation Gateway. The Federation Gateway can be used optionally to integrate the LTE or 5G network created using Magma with a mobile network operator core. Magma can be used by the wireless internet service providers to expand the cellular connectivity in rural or remote areas, and they can integrate that expanded cellular network with MNO core using this component, Federation Gateway. So this picture talks about the decentralized and distributed EPC architecture. So in general, mobile network elements like RAN and core are centralized in public or private cloud by tier 1 network equipment providers, and they are provisioned by the MNOs. For example, in a traditional cellular network built by big players, the mobile core and RAN components like radio unit, distributed unit, and centralized unit, they are all getting virtualized and run in a centralized location in a private or public cloud. Magma takes the decentralized approach. Using Magma, wireless internet service providers can build their own cellular network and integrate their network to MNO core using this Federation Gateway component. The cellular network that they build can cater few hundreds or thousands of devices depending upon the scale, and they can choose any ARM device of their choice to run the Magma mobile core. It is the new do-it-yourself model, and Magma can be run on any system ranging from M1 Mac, Raspberry Pi, or any ARM ODM systems like from companies like Sercom, Nexcom, and Hawkeye, all the way till ARM AWS instances like Graviton 2 or 3, depending on the scale. This is unlike one size fits all kind of model from some of the players for building your own cellular networks. In short, decentralized network can be built based on the population density at low cost. If more capacity is needed, more instances of AGW and radio can be spawned in a distributed fashion as shown in this picture. Now looking into this distributed EPC model, there are few benefits. You can use any commodity hardware of your choice to run mobile core and choose any radio of your choice supporting any wireless technologies like CBRS, LTE, and 5G, and even Wi-Fi. CBRS is an unlicensed spectrum and it is free in USA. You can scale out as and when needed, as mentioned here, instead of scaling up vertically. And also you are making the fault domain small. And when you watch this, it resembles the SDN model in which the control plane and user plane are separated. Here the orchestrator is like an SDN controller, and it can run remotely on an AWS cloud. Next, I would like to hand it over to Mark to discuss about the ARM engagement in this project, as well as to introduce some of our ARM ODM partner systems on which you can run Magma mobile core. Back to you, Mark.
Thanks, Govind. Thanks a lot. Yeah, that's a great introduction of the Magma project. And you've touched on a few of these points in your presentation. There's a number of ODM and partners that we're working with to enable this solution on ARM's devices in general. So this list here is highlighting the devices that were used during the 1.8 release, the latest release of Magma, which has moved the foundation project to containers. And Shubham is going to talk a lot more about the development flow that's enabled in Magma today. To capture here, what's important is, one, the core can be developed and managed in the AWS Graviton space. So from a development perspective, if you're looking at spinning up an instance of the AGW and you want to play with it, you can do that in the AWS space. So it's a great place for development. It's a great place to run trials. The next three companies that are listed here, Nexcom, Hawkeye, and Sercom, these ODMs are leading the pack when it comes to enabling the Magma core solution on their products. So these are companies that are offering off-the-shelf hardware. They've taken the initiative to install the latest Magma code. They've demonstrated it with different radio technologies. If you look at Hawkeye and Sercom, they're using their own radios or their partner radios, and they're integrating a solution that they can provide in the market. So from an accessibility perspective, you can pick up these boxes, you can download the core, and you can run the latest Magma solution out of the box. Solid Run is another ODM that provides turnkey solutions in the form of white boxes. And they're highlighted here because Connect 5G, which I'll talk about in the future slide, are leveraging Solid Run's solution, which is the ClearFog box. And the unique aspects of that solution is that it offers a 10 gigabit per second network interface in a small portable form factor that you can see in the image here. That's pretty powerful, and we'll talk a little bit more about what Connect 5G is doing with that solution. Then we've got AD-Link. So AD-Link has built a number of servers with Ampere processors. And working with Carnegie Mellon University, we were able to demonstrate the latest version of Magma 1.8 running on their server alongside other applications. So we'll go into more details about that as well. And finally, as Govind mentioned, you can run the Magma stack on a Apple M1 system. So another great development platform. Now, this picture here is just to highlight the uses of a decentralized wireless network like the Project Magma and what it offers, right? So when you think about different use cases, the first image here is of apartment buildings. So imagine that you've got an apartment building and all the users in this apartment are looking for or looking to access the internet. Well, one way you can do this with Magma is to host a Magma AGW in one of these buildings and light up a 5G or an LTE network and provide a SIM card to each one of the residents inside of these apartments. They could run this in a standalone box that breaks out and provides Wi-Fi or network or Ethernet. The main point is you don't need to run a cable from your central backhaul into the apartment to all of these separate apartment units. You can just light up this 5G or LTE network and then provide access to the tenants in these buildings. Another idea is if you're considering a ship, right? If you're on a cruise ship, you quickly lose connectivity once you move away from the port. If the ship had a decentralized wireless network set up with Magma core running, they could leverage a satellite backhaul and provide an LTE network or a 5G network on the ship for all of the passengers. Another idea is in the industrial or agricultural space, you may need to expand your Wi-Fi network to collect data from sensors that are either farther away from the center where your Wi-Fi access point is located, or you may want to offer an extra level of security. Well, with the Magma core, you could simply replace your Wi-Fi internet or network with the Magma network with LTE or 5G. This is another area that's quite interesting for us. And there's a number of other scenarios here. You know, college campuses, you may need to add extra connection points, you know, to service the college environment, and then really use a backhaul on the internet to access the internet, so they can run their own private LTE. Same with hospitals, you know, they can do that. The enterprise companies can also set this up in their environment. The rescue operations, another scenario, same with the remote areas here, where if you're in an area where there is no connectivity, if you can get access to a satellite link or to a fiber connection, then you could create your own private LTE network and, you know, provide that service to those who are in that area. All right, I'm going to take a few minutes here just to talk a little bit about what Connect 5G is doing. Connect 5G is a system integrator working in the United States, and they're looking at extending the wireless internet service provider's network with a wireless network over LTE or 5G. So what we're showing here is a small box, which can be the solid one ClearFog unit, connecting to a tier 1 radio and providing that breakout and that access to the network. So enabling a LTE network off a high-end radio with off-the-shelf hardware and the Magma core inside of it. So this is pretty interesting. And if you think about a cost structure of a scenario like this, they can leverage the CBRS band, so they don't need to pay for spectrum. Using off-the-shelf hardware makes it really easy and portable and scalable. If you need to provide a bigger pipe, you just simply expand this box and the software looks the same. So that's quite exciting, and there's going to be some announcements I'm expecting from Connect 5G. In fact, we're hoping to do a workshop very soon with them where they're going to be able to demonstrate the steps to enable the Magma stack on a device like the solid one ClearFog, and help the audience, you know, go through these steps and to show how easy it is to set this up. This next example comes from Africa, from DishNets, focused in the African market. And what they're doing with Magma is the traditional model that was originally envisioned when Magma was kicked off by Meta. This is providing connectivity in low-cost regions or areas that are underserved by the telcos today. So imagine a village in a remote location in Africa that has no connectivity option other than satellite or fiber. With the Magma core, DishNet has been able to provide a service to the community and in the form of an LTE network. So they're lighting up an LTE network and providing access to the entire village. And the connection back to the main internet is through satellite or fiber. So that's a very interesting use case. And I think we'll see more of this type of application rolling out over the next few months. Now, moving on to Carnegie Mellon University's use case. What they are attempting to accomplish is a MEC box. If you understand the principle of a MEC solution, it's a all-in-a-box network and processing power. You know, the idea of being able to take a server, connect a 5G radio to it, connect to a drone, you know, that's flying around collecting data, and have a feedback loop from that local processing unit up to the drone that's really fast and that is dynamic. You can simply light this up in any location without having to worry about MNO connectivity. You simply create your own network for, you know, reduced latency, for higher bandwidth connectivity, for reliability reasons. And this is what they're going to work on over the next year, is to create this concept of a all-in-a-box solution that includes a mobile network core. And of course, Magma allows them to do this. I'm going to pass it over now to Govind to go over the steps to create your own LTE network.
Thanks, Mark. Yeah, hello again. So now I'm going to discuss with you about the steps to create your own LTE network using the CBRS spectrum. And as I said before, it's a unlicensed spectrum and it's free to use in USA. So this is the setup that I have in my lab here. So what are the components needed to build your own LTE network? You need a radio, you need a box to run the AGW service, and you need an AWS instance to spin the orchestrator. And you need a user equipment. In my lab, I'm using a test phone to test the connectivity to internet. So what is step one? Step one is to spin an orchestrator and get an NMS page. NMS is Network Management System. So how to spin this orchestrator? I have provided the link at the bottom. You can follow the steps as mentioned in that link. The next step is to pull the AGW Docker image from Magma Artifactory. As part of 1.8 release, which happened a couple of weeks ago, we have created the AGW Docker image for ARM architecture and stored in the Magma Artifactory. You can pull that Docker image on any ARM devices that was just shared by Mark. You can choose any ARM ODM partner systems from Hawkeye, Sercom, or Nexcom of your choice and pull this AGW Docker image and run all those services in it. So the steps to bring up the AGW, again, I have provided the link at the bottom here. You can follow the steps to bring up the Docker services in this box. And the next step is to bring up the radio. So in my lab, I have a Bicel radio, but you are free to choose any radio from, it can be a tier 1 or a radio from companies like Sercom. You have to configure those radios and bring up the eNodeB software. And the next step is to create the LTE network in the NMS page that we got after spinning the orchestrator. So you have to add the AGW and the eNodeB as part of that LTE network. So with this, we have built the LTE network. The next step is to enable the subscribers and provide the cellular connectivity. So all you need is you have to get the IMSI number. It is every subscriber will be provided an IMSI number, and that number have to be provisioned through this NMS page to enable the subscriber. It is the same IMSI number that has to be burnt in the blank SIM. That is the last step. So you have to burn the IMSI number in a blank SIM and put it in a user equipment. As I said, I'm using a test phone. I have inserted the SIM with the IMSI number that I configured in the NMS page. So after that, you are good to go. You can connect to the internet. So these are some of the simple steps you can follow and build your own network. Please go through the information available in those two links. Next, I will pass it on to Shubham to discuss Magma community's work and progress on ARM architecture.
Thanks, Govind. So let me start by giving some DevOps update that we have done for enabling ARM. When we started working on ARM enablement for Magma, our first goal was to bring Magma's access gateway to the ARM platform. At that time, we already had a containerized access gateway running for x86 platform. So we started working with that. Me, Govind, Mark, and many of the community members started working on this project together. There were many library dependent that we had to fix, and all these packages that were not there for ARM, we had to build it, and we did that. And once the build was final, we need to create a CI workflow that will do all these steps in an automated way and for building our images. But GitHub Action doesn't provide ARM runners by default, so we had to come up with our own CI workflow that will create these new ARM images on AWS instances and then push to our Artifactory. So the flow that you are seeing, it's actually that how we are doing it. We are just building those images and we push them to our JFrog Artifactory and report the build status to our CI dashboard using Firebase. Okay. So a very useful thing that we learned is that we can also use self-hosted ARM runners on GitHub Actions, which work flawlessly with AWS Graviton 2 instances. But we have to manage all these nodes manually, so we didn't opt for that. If any of the community member would like to try these self-hosted runners, they can use any of the cloud vendors or third-party companies such as like Hawkeye, Tech, Nexcom, or Sercom devices for building these ARM images. They can just fork the Magma repo and test it out on their folks. For sanity testing, we are using S1AP tester, which we have developed specifically for Magma integration test. With each commit, we are doing the integration test for Magma using GitHub Actions. For development, we have used third-party tools such as SRSVAN for 4G testing and UEDANSIM for 5G testing. There are also few tools available from OpenAir interface team. For 4G, they have OAI ENB and OAI LTE, and for 5G, they have GNBSIM. All these tools are open source, which can be used for testing Magma. So OpenAir interface is currently building an ARM-based containerized S1AP tester, which will be integrated with CI for doing sanity testing in future. They are also working on 5G asset tester, which we will be used for sanity testing specifically for 5G core. And for Federation Gateway, they have already built some 4G tests, which are right now running on GitHub Actions, and its reports are regularly pushed to Magma CI dashboard. If anyone is interested in collaboration with OpenAir interface for these integration tests, they can contact Sagar or Frank from the OAI team. So many of the companies have asked us to bring Magma in a box and also include a radio. So we have already tested and deployment of an orchestrator and access gateway in a box, which can be deployed on edge locations. That's working for x86. So we have used KVM for the isolation of these components with multiple physical NICs interface. Now we have started testing the same process with the ARM platforms. We will be testing these deployments on Hawkeye, Nexcom, and Sercom devices. So hopefully that will work great. So right now, for the Magma orchestrator deployment, Kubernetes, which is deployed using Helm charts. So we deploy Magma orchestrator using Helm charts. And we are also working on new Helm charts for the Access Gateway and Federation Gateway. Alpha version of Access Gateway Helm charts are already ready. And we would love community members to try it out and help us make it more stable. For the Kubernetes cluster setup, we have Terraform code that deploys EKS cluster on AWS and then install Magma orchestrator on it. We also have some Ansible playbooks if you want to set up the cluster on your on-prem solution, and then Magma orchestrator can be deployed. Before we talk about the Magma, we will talk about the ARM-based Magma orchestrator. We have to talk about the ARM-based Kubernetes cluster. We have to build a deployment pipeline that will spin up production-based Kubernetes cluster for ARM, because right now EKS on Amazon doesn't provide us that. So because we need that, which can be used for deployment for the Magma's orchestrator. There are a few hurdles when it comes to building Docker images for ARM, specifically for the orchestrator. First is finding the right libraries that will work with ARM, and ARM team is really helping us there like fixing all the ARM related issues. Second is finding all the ARM dependent images, such as PostgreSQL, Elasticsearch, Fluentd, and all these extra things that our orchestrator depends on for enabling all the functionalities and features that we have. So once our build is final, we have a final build ready for the ARM platform. We will develop a new CI pipeline that will build all these ARM images and push them to our Artifactory for the ARM. So we have a very active community on Slack, and all our Zoom calls are public and recordings are shared on YouTube. We welcome everyone to come join our calls and join our Slack groups. New contributors are always welcome, and we would love to assist them in onboarding all of this process. Thank you. Back to you, Mark.
All right. Thank you very much, Shubham and Govind, for assisting in this presentation. I think this wraps up our presentation for today. Thanks, everyone. Thanks for joining. Thanks for listening in.
Thank you, everyone.
Thank you.